So what we're going to do is find the electric field at a point P, and point P is to the right of the midpoint of a long positively charged rod. Here's our rod. Here's point P. It's off to the right, and it's from the center of it. Our rod has uniform charge density. That means that the amount of charge on the rod is evenly distributed over the whole length. So one part doesn't have more charge than another part. It all has equal amounts of charge. Our first step in this process is let's divide the rod into many small elements of charge. And this is like what we did in the previous slide when we were constructing a continuous charge distribution. We're going to consider that this rod has many small pieces of charge. When we get started in our process, we take one such element of charge and we shade it in. So we show our dq on the picture. So draw, show, dq. That's step one in our process. Our next step in the process is to consider our element of charge and ask what electric field does this little piece of charge make at point P. Since this is a little bit of charge, it makes a little electric field. We call that an element of electric field. And regular electric field, due to a discrete charge, would have a symbol of E. An element of electric field has symbol dE. It is a vector because it has a direction. So our charged rod is positive. That means the electric field created by dq will point away from the rod. So this is what that little element of charge is going to look like, dE. dE is a vector, so it has components. Those components are going to be the x component and the y component. So we should show those components as well. So the x component is going to be to the right, and the y component is going to be down. So those are the x and y components of that little element of electric field. Here is a good place to point out that when we choose our value of dq, we should never put it right at the top, we should never put it right at the bottom, and we should never put it in the middle. When we pick any of those three places, sometimes we lose some of the symmetry of the problem. So in general, when you draw your dq, pick it close to one end, but not exactly at the end, and definitely not in the middle. Okay, now we've got step two done. We've drawn the element of electric field and we've shown the components. Our next step in the process is to write an expression for the magnitude of our element of electric field dE, and then to break it into components dEx and dEy using our trigonometry. So we probably remember that electric field due to a point charge is K times Q over R squared, where Q is the size of the charge, R is the distance between the charge and the point. Same holds true for an element of electric field due to an element of charge. dE, the little bit of field made by this little bit of charge, is K, Coulomb's constant, times the little bit of charge divided by R squared. Okay, since we've put R in our equation, we better put R in our diagram. And R is the distance between our element of charge and our point P. So here's our R right here. All right, to find our components, we know that we need to use some trigonometry. I'm going to call this my angle theta, which makes this my angle theta. So my dEx is adjacent to my angle. That means dEx is equal to dE times cosine theta. And my dEy equals dE times sine theta. All right, so to find my dEx, I need to figure out dE and cosine theta. To find dEy, I need to figure out dE and sine theta. Step 4 is going to take us a little bit of time. First, we'd like to identify the parameters and then write dq in terms of whatever parameters are appropriate. We've already got a coordinate system on here. X is horizontal, Y is vertical, and we've placed the origin at the center of the rod. Okay, so there's our coordinate system. So then let's call X the distance from the midpoint to point P. So X is the horizontal distance. From the rod to point P, from the midpoint of the rod to point P. What we might notice is that no matter where we have drawn our dq, that value of x would always be the same because it's the horizontal distance. So next to x, I'm going to put constant in brackets because constants and variables are going to be very important as we integrate. Y is going to be our distance from the midpoint to our element of charge dq. So y is our vertical distance. And that's from the midpoint to dq. What we'll notice here is that this value of y does depend on where we take dq. dq was up here, y would be bigger. dq was down here, y would be smaller. So y is a variable in this problem. Okay, what next? We've put r in our picture, so let's recognize that r is the hypotenuse of a right-angled triangle. That means that r squared is equal to x squared plus y squared. Or we could take the square root of both sides. R is x squared plus y squared to the power of 1/2. Next, in our expressions for dEx and dEy, we see that we have cos theta and sine theta. We've drawn theta in our diagram. Let's also write down what cos theta and sine theta are equal to. Cos theta is adjacent over hypotenuse. So that's x over r. Sine theta is opposite over hypotenuse, or y over r. Okay, now we've sorted out all of the parameters in this problem. We know ultimately we're going to be integrating, and we'll be integrating in terms of a variable. And what else do we know? We have our element of electric field in terms of an element of charge. We'd like to tie dq to the parameters of our problem. Let's look at the next slide to do that. Our next step in the process now is to write dq in terms of the parameters of the problem. So that's going to take us back to uniform charge density. If we ask about charge density, the important or the dimension of our object is important. If we have a line of charge, this is a one-dimensional rod. So this picture specifically is one-dimensional. This is a line of charge. So here, our charge density has a symbol of lambda, the Greek letter lambda, and it's the total charge divided by the total length. So yeah, let's leave that there for a moment. So the charge density in a one-dimensional situation is lambda equals charge over length. For a plane of charge, so this would be a two-dimensional situation, the charge density has a symbol of sigma, and it's the total charge divided by the total area. Sometimes this is called area charge density or surface area charge density. If we had a sphere of charge or a box of charge, something in 3 dimensions, our charge density now would have a symbol of rho, Greek letter rho, so like a curly P, and it's the total charge divided by the total volume. This step 4 is a general step for any approach to any problem. So whichever problem we do, we have to write dq in terms of the parameters. To know which of these to use, we have to look at what we have. We have a one-dimensional line of charge, so we have to use this top expression for lambda. So we're trying to figure out what is dq. dq is an amount of charge. So our expression here says charge density is charge divided by length. That tells us that charge equals density times length. Okay, just a little cross multiplying there. So let's apply this idea to our dq. dq is the amount of charge we're trying to figure out. So dq is the charge density lambda. We're going to define up here that lambda is our charge density, which is the net charge divided by the total length. So dq is lambda times the length. Now, the length is a little bit interesting. Let's look at this rod. And what is the length of this rod? Or the length of our element of charge. What is the length of our dq? So first I'll draw it on my diagram. The length of dq is from here to here. We might notice that this length is a little bit in the y direction. So the length of this rod could be called dy because it's a little bit in the y direction. So dq equals lambda times dy. This is kind of an important point. When you have a vertical rod, you use dy, so your length is vertical. If you have a horizontal rod, you use dx because your length would be horizontal. If you had an arc or a circular rod, you would use a little bit of arc length. These things are going to come back around and we'll have to use these later. So what we use here for our expression of length depends on the geometry of our rod. Anything vertical is dy, anything horizontal is dx, anything circular is ds. Okay, so now we have dq in terms of the parameters of the problem. Here's our charge density, and this is the length of the rod, and we know y is a variable. So here's a neatened up summary of what we talked about on the previous slide. X and y are our parameters of the problem. X is the horizontal distance, y is the vertical. R is the distance between dq and our point, and r is equal to the square root of x squared plus y squared. We can use those variables, x, y, and r, to write cosine theta and sine theta. We know that charge density is charge over length, so our little bit of charge here, dq, is the density, lambda, times the length of our little bit of charge. Our length of our little bit of charge is all in the y direction, and it's only a little bit of y, so we call that dy. So here's our expression for our charge density because we have a vertical rod. Okay, step 5, let's write expressions for dex, so the x component of our element of electric field, and dey, the y component of our element of electric field. And what we're going to do is we're going to put all of these things into these expressions. Let's get going with dex. Dex is equal to de times cosine theta. De is equal to k times dq over r squared. Cosine theta is x divided by r. In the next line, we'll put in that dq is equal to lambda, the charge density, times dy. That's times x in the numerator. In the denominator, we've got r squared times r. That gives us r cubed. Let's pause here for a moment and recognize that even though we're finding the x component of the element of electric field, we still have dy here. That's because dy comes in as the length of our element of charge. So we can have a length of dy to go with an x component. This is completely legitimate and this is correct. A lot of times students email me and ask if that's a mistake. It certainly is not a mistake. Okay, let's fill in what we mean by r. dyx. R is equal to x squared plus y squared to the 1/2. And remember, our r is cubed. So our final expression for dex then is k times lambda times dy times x divided by x squared plus y squared. When you have an exponent to an exponent like this, you multiply the exponents, so that's to the 3 over 2. So this is the x component of our element of charge dE. Next we'll do dEy. Let's write the y component of our element of electric field next. So this is our y component. dEy is equal to dE times sine theta. dE is k times dq over r squared. Sine theta is y over r. So we've got k times dq, that's lambda dy times y. We've got r cubed on the bottom. So dEy is equal to k times lambda times dy times y divided by x squared plus y squared to the 1/2, which is all cubed, to give us x squared plus y squared to the 3 over 2. Okay, now we've got our x and y components. Let's write those neatly on the next slide and see where we go from here. Now let's just make sure we remember what we've done here. This is dex, this is dey. Those are the components of a little bit of electric field, which is made from a little bit of charge. In order to get the total electric field, we have to add up the x component due to each little bit of charge along the whole line, and we have to add up the y components due to each little bit of charge along the whole line. If we're adding them all up, then what that means is we have to take the integral. So the x component of the total electric field is the sum of all the little x components. The y component of the total electric field is the sum of all the y components, or the integral of dEy. Let's go to this sentence before we carry on with our integration. Here we say use symmetry if applicable. So this is saying, can you look at the picture and can you tell that any component of electric field is going to sum to 0? So if we look at our picture here, we have that the top half of the rod has an electric field with elements that point down and right. So no matter where you draw your DQ on the top half of the rod, the x component will point right and the y component will point down because it points away. If you look at the bottom half of the rod, you would see that any component of electric field you draw would point up because it would be away from a charge. It would point up and right. So since the top half has y components that point down and the bottom half has y components that point up, the total electric field in the y direction would be 0. This sort of thing is only going to be true, like we'll get components equal to 0 when we have high degrees of symmetry in a problem. We'll go through some examples like this and hopefully you'll get to see where it comes from. If you don't catch the symmetry, it's okay. Your math is going to show that the y component will sum to 0. So if you can see the symmetry, if for example this were a test problem and you said EY equals 0, due to symmetry, that would be considered correct. If you didn't catch that symmetry and you went through the process of doing the integral and you found EY equals 0, you'd still be correct. One important thing I'm going to point out here is that EY is equal to 0. DEY is not 0. So if you write on a test DEY equals 0, I'm going to mark it wrong and I'm going to take off a bunch of points because that's not true. DEY is given by this expression up here. This is not 0. When you get 0 is when you add up all of the bits of DEY. Okay, so it's an important distinction. Okay, let's move to the next slide and let's go ahead and do our integral. So let's find the x component first. So we'll start by saying EX is the integral of DEX. Now we'll fill in what we had for our DEX. K times lambda times x times dy divided by x squared plus y squared to the 3 over 2. Okay, first thing we can do is we can take our constants out front of the integral. So k is a constant, lambda is a constant, x is a constant. Remember, this value of x is the same no matter where our value of dq is. Everything else is stuck inside the integral. So we've got dy divided by x squared plus y squared to the 3 over 2. If you're wondering why you can't take the denominator out, there is an x in it which is constant, but it's coupled with the y, and the y is variable. So all the variables have to stay inside. We know when we integrate over appropriate limits. So we go from y initial to y final. So now is a good time to ask, what are the limits of the integration? In general, the limits of the integration are from one end of the rod to the other. So if we look at our picture, we'll identify the two ends of the rod. Here's the bottom end. Here's the top end. We're going to remember that we picked our origin at the center. So we'll start at the bottom end of the rod. This is y initial. Okay, this part is pretty important that you get this right, because if you mix up the limits, you're not going to get the correct answer. This is 0. This is where the origin is. The rod has a length of L. So from here to here is length L. So Y initial is at the bottom half of the rod. The middle of the rod is 0, so this bottom end is at minus L over 2. Y initial equals negative L over 2. Y final, where we'll stop, that'll be at the top of the rod. The top of the rod is halfway above, it's half the rod. So the top of the rod is at a position of Y final equals plus L over 2. So this is Y final. Sometimes people get a little astray here and they want to put the limits in as 0 to L, but that just doesn't match the picture. The bottom of the rod is not at Y equals 0 because Y equals 0 is at the middle of the rod. So your limits have to match the geometry of what you drew in your picture. Okay, so let's add that into our expression. So our integral is now k times lambda times x. We're integrating from minus L over 2 to plus L over 2 dy over x squared plus y squared to the 3 over 2. Okay, if you love integrating, by all means, go ahead and integrate this expression. I will look this up in a book. So I would not expect you to do this integration by hand on any sort of test or assessment. If you prefer to do it, no problem, but I'm not going to ask you to. So your result is k times lambda times x times 1 over x squared times y divided by the square root of x squared plus y squared. And that's evaluated at our limits of L over 2 and minus L over 2. Okay, we'll keep going with this now on the next slide. So to carry on, we have to fill in our limits of our integration. So we get k times lambda, an x squared in the denominator, x in the numerator. So one of those cancels, and I'll pull that x out front. So first we'll plug in L over 2. L over 2 divided by the square root of x squared plus y squared. Y squared is L over 2 all squared. So the L squared and the 2 is squared to give 4. And then we subtract the value with the minus L over 2 subbed in. So that's minus L over 2 divided by the square root of x squared. Negative L over 2 squared is still plus L squared over 4. Okay, there's our expression. Let's just neaten it up a tiny bit. L over 2 minus L over 2 gives us plus L. The denominators are the same there. So we're left with k lambda times L divided by x times the square root of x squared plus L squared over 4. So there's the x component of the electric field due to this long line of charge. One thing I'm going to point out here, depending on how you pick your limits, you might get a funny plus or minus here. You've got to be really careful to apply your common sense to your result. We see that the x component of electric field points right. We know the answer should be positive. If you got a negative answer because of how you picked your limits, it's absolutely fine to say, this came out negative because of how I picked my limits, but I know that the x component is positive. That's absolutely legitimate, and that's applying some physics to the situation. Okay, we've already said that the y component is going to be 0, but let's go through the process of calculating it anyway. So for our y component then, we know that our total y component is the sum of each individual y component. So our next step is we'll fill in what we have for the individual y components, our dEy, k times lambda times y times dy divided by x squared plus y squared to the 3 over 2. We can take our constants out front, so k is a constant, lambda is a constant, y stays inside, dy stays inside, and then x squared plus y squared has to stay inside to the 3 over 2. We need to apply the limits of our integral. They go from y initial to y final, just like in the previous step. And we'll use the same limits that we did previously, so from minus L over 2 to plus L over 2. You have two options here. You can work out the integral for yourself, or you can look it up in a book. I shall choose to look it up. And what we get for the results of our integral is our k lambda is outside, and we're multiplying by minus 1 over the square root of x squared plus y squared. That has to be evaluated at L over 2 and minus L over 2. So we'll put in plus and minus L over 2. We get k times lambda outside of minus 1 over the square root of x squared plus L over 2 squared is L squared over 4. I've written it a little bit small, but hopefully you can still see it. And then we're subtracting minus 1 over the square root of x squared minus L over 2 all squared is still plus L squared over 4 equals 0, which is what we expected from the symmetry, so we're on track there. So just to finish up, we're going to have to evaluate the signs, make sure we're comfortable, and then write our answer as a vector. So as I mentioned, now we have to use our common sense. We have to look at the problem and make sure we have the right signs. When we look at our electric field, we know it points away from the rod. So at point P here, it has to have an x component to the right. So EX points right. It is positive. So now we'll finish off by writing our electric field vector. E is the x component in the x direction plus the y component in the y direction. So E is equal to k times lambda times L divided by x times the square root of x squared plus L squared over 4 in the x direction. One additional step you could take here if you wished. You might remember that lambda is Q over L, so you could fill in that Q is equal to lambda times L here, and that would give you your electric field equals K times Q over X times square root of X squared plus L squared over 4. That would be an acceptable thing to do as well. Okay, so this is the electric field, a distance from the midpoint of a vertical rod. How about for a homework problem? You try and find the electric field above a horizontal rod. So twist your geometry here by 90 degrees to the left and see if you can work through the problem.